In this example, we are going to calculate the heat transfer through a wall which is made from different material. In other words, it is a composite wall which is made from different material A, B, C, D, E, and F. We are going to calculate the heat transfer from the inside of the wall to the outside of the wall. The temperature inside the wall at the inner surface of the wall is 300 degrees Celsius. The outer surface is 100 degrees Celsius. Then we are going to calculate the heat transfer through this wall. The dimension of the wall is given: 5 meter high, 8 meter long, and the thickness is 0.22 meter thick or 22 centimeter thick. The thermal conductivity of various materials is given in terms of watt per meter degree Celsius. Ka, Kf is 2 equal to each other, Ka, Kf. Thermal conductivity of A and F. Kb is 8, Kc is 20, and Kd is 15 watt per meter degree Celsius. And thermal conductivity of material E is 35 watt per meter degree Celsius. And it is also mentioned that the temperature at the inside and outside is maintained at uniform temperature. We have this sentence because it helps us to make an assumption about the condition of the problem, which is in a steady state condition. We don't have any change with time in the temperature in the inside and outside of the wall. And also it is one-dimensional heat transfer. Then what we are going to calculate, assuming heat transfer through the wall to be one-dimensional, it's also given, so it can have with this assumption as well. Then the rate of heat transfer through the wall, we should calculate that, Q dot, total Q dot. The temperature at the point where the section B, D, and E meet. B, D, and E meet. It means this intersection. And the third part of the question is the temperature drop across the section F. Temperature drop from this interface up to this interface through this section. And it is also given to us to another sentence to help us for our assumption. Disregard any contact resistance at the interface. It will also help us to solve the problem. First, let's see what can be our assumption. 1, a steady state condition. As I told you, we don't have any change in the temperature with the time. The inside and outside temperatures will be constant during this heat transfer. One-dimensional. It is also according to the question. Thermal conductivities are constant. It is also mentioned in the question, which is constant. Thermal contact resistance at the interface are disregarded. This is also according to the question. It helps us to ignore those thermal resistance, and only we have thermal resistance through the material, not at the interfaces. And properties which we have are thermal conductivity of each material. Thermal conductivity of material A and F are equal, and for the other material you can see here. Okay, after these properties, let's analyze the question. We can, instead of calculating heat transfer for all of the wall, we can select a representative surface area of the wall. So we just choose a 1 meter length of the wall. Here is 8 meter. We choose 1 meter of this wall, and also we have the thickness here for the wall. So, and also in this direction the size of the wall is 12 centimeter. So the representative surface area for our calculation is equal to 0.12 meter square. So we just calculate for 1 meter thickness of this wall, not 8 meter. And also in this direction we don't calculate for all of the length of the wall, we just calculate for 12 centimeter. Then the thermal resistance network for the individual thermal resistance are, according to material we have here, are like this. We have only conductive thermal resistance in the wall. For material A, we have R1. For these three parts in section 2, we have two material, but we have three parts, so we have three thermal resistance, R2, R3, R4, three conductive thermal resistance. In section 3, we have two thermal resistance for part D and part E, because we have two different material. And for the section 4, we have only one material and one thermal resistance. Then let's calculate the conductive thermal resistance for all of these material. It's easy because you know, this is like a conductive thermal resistance for plane wall. We have this equation, thickness of that wall divided by thermal conductivity of that material times the surface area of the heat transfer. So the conductive thermal resistance for section 1, which is made of one material A, is equal to thickness of that material divided by thermal conductivity of material A times the surface area. Total surface area, representative surface area, is made from this material. So the thickness is 1 centimeter. The thermal conductivity of the material A is 2. The surface area of heat transfer is 0.12 meter square, which is representative surface area. As I told you, we just choose a small part of this. Let me show you. We are just going to calculate for example, this much. Sorry for handwriting. Only for this. This is A. We are going to work on this A. And you can see here is 12 centimeter in this direction. 1 meter. This is 1 meter. Then we have 1 meter, and in this direction is 12 centimeter. Then this is surface area of heat transfer for material A. Then to calculate R2 and R4, we have again thickness divided by thermal conductivity of material C times thermal conductivity times surface area of this part. As you can see here, the dimensions are same for these two parts, also the material are same, so the thermal conductivity resistance, conductive thermal resistance for these two parts is also same. We can calculate like this. The thickness 5 centimeter, thermal conductivity for material C is 20. Surface area of heat transfer is 0.04. You can see here 1 meter times 4 centimeter. Heat transfer is in this direction, so surface area should be calculated in this area. We have a similar calculation for R3 or RB, thermal conductivity of material B. A is same like C. K is different, or thermal conductivity of material B is 8. The thickness is similar to. Again, here you can see the thermal resistance for R5, which is for the D, material D here in the wall. We have the thickness 10 centimeter or 0.1 meter divided by K of the material D, which is 15, times the section or surface area or per surface area of heat transfer for material E. You can see here we should calculate the A in this direction, which is 1 meter times 6 centimeter gives us 0.06 meter square. Result of this calculation will give us the R6 or RA thermal resistance of the material A. We can follow the same equation for material F, which all section 4 is made by this material. Again we have conductive heat transfer, so we can use this conductive thermal resistance equation to calculate thermal resistance of the material F. The thickness is given 6 centimeter. K or thermal conductivity of material F also is 2, and the surface area of heat transfer is whole representative surface area, which was 0.12 centimeter squared. Finally, after calculation, we will have the thermal resistance for material F. Then we should calculate the total thermal resistance of the wall. Before that, we should simplify this arrangement of the thermal resistance to most simple form. So then first we should calculate the equal R for this part, because they are in parallel arrangement, and also you should calculate the R equal for this part because they are in parallel arrangements. So they are equal for mid 1. It means this part is equal to 1 divided by R2 plus 1 divided by R3 plus 1 divided by R4. Then by substitution of this value, we will have the R equal for mid part 1 for this part or for this part in the figure. Then we should calculate the R equal for this section of the wall, which consists of two parallel conductive thermal resistance R5 and R6. So R divided by R equal mid 2 equal to 1 by R5 plus 1 by R6. By substitution the value of R5 and R6 and solve this equation, we will have the R equal for this section of the wall. Then finally for this part we will have actually something like this. Let me draw this for you. After this we will have something like this. This is R1. Then for this part we have R equal mid 1. Then we have here is R equal mid 2. Then R7, and this is T1 from T1 to T2. This is R total. To calculate this, we should only simply add all of this to each other. So we will have R1 plus R equal mid 1 plus R equal mid 2 plus R7, because they are in series arrangement. by substitution the value for all of these thermal resistance, we will have the total thermal resistance of the wall. Then to calculate the heat transfer rate through the wall per section of area, which was our assumption, representative area was 0.12 meters squared. We should use this equation. You remember this equation for rate of heat transfer through the wall. We have a steady state condition and one-dimensional heat transfer. Q dot equal to T infinity 1 minus T infinity 2 divided by R total. So T infinity 1 is 300 minus 100 T infinity 2 outside the wall divided by R total we have calculated here. This heat transfer is only for that section area we choose for as an assumption. Then to calculate the all heat transfer through the wall, we should multiply this heat transfer through the all surface area of the wall. So the surface area times 5 times 8 divided by 0.12. The total surface area was 5 times 8 meter. If you remember in the question it was given 8 meter in this direction and 5 meter high. So 5 times high will give us the total surface area of the wall. So to calculate total heat transfer, we should divide this total surface area to the our assumed surface area. Then we will have this heat transfer, rate of heat transfer through the wall, entire wall. Then to calculate the temperature at the intersection between the materials D, E, and B in this point, we should use this equation actually. Q dot equal to T1 minus T divided by R total 1. Then by rearrangement, we will have this. This is temperature at the interface, which T equal to T1 minus Q dot times R total 1. But what is this R total 1? R total 1 is R1 plus R equal mid 1. In other words, here R1 and the thermal resistance for this. Thermal resistance from this point to this point. We have temperature for this surface. We don't have temperature in this point, so we should use that equation, this equation here, to calculate the T. So T1 is the temperature at the inner surface, 300 degrees Celsius, minus temperature at this point, we don't know how much is it, divided by R total from this surface to point B, this surface. So what we have the for thermal resistance between these 2 points is summation of the thermal resistance for these 3 parts, for this section, and thermal resistance for this. In other words, R1 plus R equal mid 1, which is R equal mid 1 is equal to this value we have calculated already. So by rearrangement of this equation, as I told you, we can calculate the temperature at that interface, which is 263 degrees Celsius. Then to calculate the temperature drop across the section F. How much is temperature dropped through this material F? How we can calculate that? By this equation, Q dot equal to delta T divided by R7. Delta T is unknown. By rearrangement of this equation, we can calculate the delta T. Delta T is unknown. We know Q dot or rate of heat transfer through that section, and we know the thermal resistance of that section. Then by substitution the value for these parameters, we can calculate the temperature drop during that material. Actually, if you remember the previous sections, we had this equation. When heat is transferred through the medium, the temperature will drop in that medium or material due to the thermal resistance in that material. So we can calculate temperature drop of that material or by multiplying the heat transfer through the material times the thermal resistance in that material.